Hello everybody, and welcome to today's Code Presents. My name is Otto, and today we are going to talk about maximizing C# performance. We're going to look at some high level advanced coding patterns, if you like, for very high efficiency apps. So essentially for applications that would benefit from having patterns implemented that will allow them to run certain algorithms, run certain patterns, and so on very efficiently, especially in applications, business applications, where we are dealing with a lot of information, with a lot of data. About me, my name is, as I said, my name is Otto. I'm a senior software developer at Code. Been with Code for, I think, over 10, 11 years. I'm also a professor at the University of Houston. I've been teaching there for, this is my 10th year, continuously. Diverse programming classes, everything from C++ to Java, JavaScript, Python, everything you can potentially think of. And in my spare time, when I'm not dealing with computers, when I'm not dealing with code, I am a powerlifter, and I do have 2 world records in the bench press. But enough about me, and let's get into it. We are, as I said, Code, the Code group. We have 30 years of our motto is helping people build better software. We have multiple divisions within Code. We have Code Consulting, which is the division I'm with. We have Code Staffing. We have Code Magazine, as you might have heard of, and we also have Code Training. We are now also offering AI consulting services. I would recommend, if you're interested, to check out our executive briefing offer at codemac.com/executive briefing or general@/AI with information about the AI services that we offer. Today, what do we have on the agenda? We start with a little introduction that we just did. We also are going to look into different modes and data structures and algorithms and other mechanics that we can utilize to make our .NET, our C# code more efficient and better performant in certain situations where this is appropriate. We're going to look at loop cascades, span slicing, and substrings, some concepts called array pooling, zero copy techniques, structs of arrays. We're going to see what Stackalloc is. We see how and why or when we should avoid LINQ, and general garbage collection optimizations. Now, with the introduction, I want to also highlight that a lot of this stuff that we are discussing now is not just C# desktop apps, WPF, WinForms, or whatever, but also applicable to Blazor. And we'll see that we have a few examples specifically for Blazor, since Blazor also runs C#, where we can make use of these techniques, and more so applicable to Blazor at some point, because Blazor as a web application has additional limitations and performance bottlenecks that a general typical desktop application does not have. For instance, all the resources that a desktop application can draw for, you're kind of limited to a certain extent if you have a web application, because you'll run in the sandbox, if you want, of a browser, and whatever the browser has access in terms of resources, your application will have access to those resources. So we will see an overview over these high performance coding techniques, some outline of some key topics, and some examples how this is particularly important in optimizing Blazor applications. Now, before we get more into it, I want to also highlight something, that these are particular things that we can use and utilize in situations where appropriate, right? So this does not mean we want to apply all of these techniques to every single one of our business applications. That is not something that I would like to convey here, because a lot of times our business applications are performing just fine, right? If I have a grid and I have 100 records in this grid, or a list, and I have to show these, then it's most likely performing just well, unless I did something really bad in the implementation, but everything, is working well. I have no need of introducing additional performance techniques, because if a grid or a list responds in half a millisecond, the user is not going to see any difference if that responds in a quarter of a millisecond, right? So the perception of the user in that regard is negligible. It doesn't really affect the performance. However, if we have business applications where we have grids or lists, and we have thousands of records, 10,000s of records, and we have hundreds of columns, for instance, whether that be a desktop application or a web application, it doesn't matter. We're going to run into some sort of bottleneck at some point, right? Not only do we have to probably already implement some sort of performance-driven visualization and rendering, we probably have to virtualize the list and so on, but on top of that, we probably have to do something that makes the rendering, well, not only the rendering, but also the data management of that component a lot more manageable. So these techniques are for these scenarios. When you do have a bottleneck, when you do have something that doesn't perform well, when you are dealing with a lot of information, when you are dealing with a lot of data, these kind of scenarios, we want to introduce some remedy that you could try and make your application better performant at that point. Loop cascading. One of the things is with loops, we all use loops all the time, which are very handy, very common, but a lot of times underestimated on how much overhead they do add. And we're going to see examples and strategies of what we can do in these situations. The pitfall is, like I said, the underestimation of nested looping. Loops, especially when you have multiple nesting inside of your loops, increase exponentially in time. So you have a double nested loop already O of n square in terms of processing time. It does not increase linear. So if you add another loop nesting to it and another one, it's not a linear increase in time, it's an exponential increase in time. And so we want to avoid that. We want to make sure, hey, can we avoid this loop nesting? Can we leverage these loops out? Do we have to loop inside another loop, or can we go a different approach? We also, a lot of times, create temporary objects, which increases garbage collector pressure. With every additional loop where we allocate more variables, remember we are in .NET, we have automatic memory management, so garbage collection is going to happen automatically. And the more we allocate, the more we have to automatically deallocate. So the pressure on the garbage collector increases. And then with that, the more loops we have, the more cascaded our loops are, the more temporary objects we do create, the poorer our cache utilization is. We will have more cache misses, and we have the CPU fetching data from the slower main memory rather than from caches. So what can we do? Well, we want to separate the problem into individual independent operations if we can. Process the data in different orders maybe. We can look at if we have cascaded loops, like let's say a double nested loop of a grid. We can check, is it better performant if we do row major order or if we do column major order. It just depends how your data is aligned and allocated. Sometimes we can use dictionary or sets for efficient lookups. Dictionary lookups are a lot faster than looping over a collection of items and finding something. And if possible, we could leverage parallelism. We can use parallel iterations to handle independent iterations simultaneously, if we, for instance, have multi-core processors at hand that we can use. So, for example, we have on the left side a simple double-nested loop that loops over a list and then over another list and checks two keys if they are matching. And if we have a match, then it does some operation. That simple double-nested loop, that is of O(n) square, we could reduce to O of n if we were, for instance, create a lookup of the second list first, and then only loop over the first list and check with a lookup on that second list. And already we have decreased our complexity by 1 magnitude. We can also further go into parallelism here, and instead of having just a for each, we could have a parallel.forEach. and try to find the matches in a parallel order. If that is possible, then of course we can do that. Of course, not every single application or every single part where we have nested loops is applicable to breaking it out into parallel loops. Sometimes the loops are dependent on the result of the previous one, so it's not a technique you can always apply, but if you evaluate the problem, then that is definitely something to consider. The next thing we want to look at is span slicing and substrings. This is very interesting because we're going to look at what span of T and memory T is. We're going to see the advantages, and we're going to have another small example of how to do this and when to do this. We want to use span of T and memory of T if we want to manage contiguous regions of arbitrary memory. We want to do that without having to create additional copies. And for those who don't know, strings are immutable objects. So in C#, but not just in C#, in other languages too, like in Java, strings are essentially immutable. So you cannot change a string, which means if you have a string and you change it, you might think you're changing a string and it's the same object, but in fact it's not. It is a new object, right? So you will say, hey, I have a string and I add another character to it, or I concatenate two strings or something. This is not operating on the same object. Every time you modify a string, it will create a new string in memory, reallocate your pointer from the stack to it, and the garbage collector will pick up the old one. So all of that handles or is handled under the hood. We as programmers don't see it. For us, it is more convenient to use strings as if we can modify them, right? But under the hood, like I said, this is not the case. And therefore, we want to avoid these heap allocations, which are performance critical scenarios if we have a lot of them, right? So we want to use something where we don't have to allocate and deallocate every single time we need to break up strings into substrings or create a lot of strings from a parsed CSV file, for instance, or something. We would like an approach where we do not have this constant allocating and deallocating of little objects in memory. Span T avoids heap allocations. It allows us or it represents a contiguous region in memory. It is stack allocated. Therefore, span T is not suitable for asynchronous operations, whereas memory T is. And what a span of T or a memory of T really is, it's more of like a view onto the original object in a certain region without creating a new sub-object from it. Right? So you keep the original object and you just create views onto that object without creating anything new additional in memory. Memory of T is allowing to create slices of data that can be used asynchronously. It's not restricted to the stack, and if need be, memory T can also be converted to stack of T. We do have significant performance gains from that because we do not have to create substrings. We do not have to create any strings if we create spans. We have reduced memory allocations because of that. We have potentially improved safety. We do have bounce checking, for instance, that can protect us against certain programming errors, like buffer overflows, for instance. And we are very flexible and versatile with it because span of T can represent various data types, including arrays, strings, or even unmanaged memory. It's a very powerful tool in a wide range of applications, from low-level memory manipulation to high-performance data processing applications alike. For instance, a practical example, let's say we have a CSV file that we need to parse. We have John Doe with an email address in a CSV line. And this is a simple example, right? Imagine you have CSV files with 50 different fields that you need to parse. And first name, last name, and email could be parsed out from this line by substring and tell the substring, hey, from 0 to the index of the first comma and so on. We create 3 substrings. And then we have these 3 strings that we can use to, for instance, create reports or whatever we need them to use for. But that creates, 3 additional objects in memory: first name, last name, and email. And now imagine you don't do this one time, you do this 100,000 times, and not just for 3 fields per record, but for 50, right? So suddenly we have millions of substrings in memory, right? Not good. Obviously, that is going to produce some overhead, and depending on how fast this needs to be done, could become a bottleneck. So instead, we could create spans. We, say we want a view onto this original CSV line from here to here. We put it into first name, we did put it into last name, put it into email. So that is a slice of that string. That is not an additional object. There is nothing that gets allocated for it, and the garbage collector does not have to pick that up, right? So that is a lightweight representation, and it represents the exact same thing as the substring. If for whatever reason we do need a string, an actual string object from it, we can always call toString on it, and it will create that string object for it. If you, for instance, have, I don't know, a report that you want to print of one of these records that you just worked with, and you had to parse all of it, find whatever you needed, you found it, and then you need that one record as a string for a report library that requires you to give it a string because it doesn't work with spans, you can do that, right? You can just say toString on these variables, and it will give you that as a string. Very powerful technique and very handy if that is the bottleneck, right? If that memory creation of lots and lots and lots of records is something that becomes problematic. The next thing we want to check out is array pooling. Also a technique that is not very common, but also it is very powerful. We want to check out what it is, see some benefits for it, and also see a little implementation example of how to use it. The concept of array pooling essentially is, let's reuse arrays rather than creating and destroying them, right? Just like with any object in .NET, anything that gets created needs to get destroyed. Garbage collector then picks something up if it's no longer needed. And if we do work with a lot of arrays, especially small arrays, the garbage collector becomes very busy, and we have to allocate and then deallocate a lot of times. And in order to alleviate that pressure on the garbage collector, we can say, you know what, there is a pool of arrays that is pre-allocated, that's just available in a predefined manner, and we can just rent arrays from there and say, hey, I need an array, I'll take it from there, and I don't have to allocate it, it's already allocated, I'm just taking it from the available arrays that I have, and when I'm done, I'm not destroying it, I'm giving it back to that pool, right, and back into this pre-allocated area of memory. And I increase my processing and my memory performance because I have less to worry about in terms of allocation and deallocation. For instance, let's say Blazor component needs to process a large data set, a graph or a grid of some sort. Maybe there is a need of sorting, filtering, other ways of transforming arrays of data. Anytime I want to normalize something, transform arrays, I will create new arrays, run another transformation on it, another normalization on it, new arrays, that sort of stuff. We could create many arrays, also many temporary arrays, if that was done conventional way with regular arrays. However, we might want to alleviate this problem with, like I said, having arrays available already predefined to us, and we just rent space from there and say we want some array of a certain size from this pool, we'll use it and then return it. As a little example, we have here an example where we have an array pool where we can rent a certain length of an array from this pool. And with this, it allows us to say, you know what, whenever we are on the first arrow in need for an array, we will rent that. And as you can see in the end of that code part, we have to return it again, right? So you're not deleting it, you're not freeing up that memory, you just have to make sure you return that array back to the pool. And once I have an array rented, I can use it as if it is a regular array, so the usage doesn't change. I will just say, you know what, I need an array, then I'm renting it, I'm using it, and when I'm done, I'm returning it to the pool. I can resize if necessary. I can minimize the garbage collector pressure with it because I don't have to wait for the garbage collector to pick up very large arrays, even temporary large arrays if they're created. And that way we're making it a lot easier on us, especially if this happens in a rapid fashion. Think, for instance, anything that has to do with render graphs, right? If you have a graph that has hundreds or thousands of data points that are in a certain array, the graphs are bound to these arrays, and then you want to modify this graph and the array changes. You need a new array, maybe the array size even changes, you need a new array, maybe the graph is animated. For every frame it has its own array that gets created and then deleted and created and deleted. That's a lot of array creation and deletion that needs to happen in very quick order. So therefore we're going to use array pooling for that and save ourselves some overhead by not letting the garbage collector collect any work or any objects in that process. Very cool technique, but like I said, also something that you will have to evaluate the situation for and determine, is this an appropriate scenario where this is beneficial to me, where having too many and too large of arrays that are temporary, for instance, and getting created and destroyed, is that a problem? And if so, yes, I will try this technique and see if it helps me. If that is not even, if I'm not even using any arrays, or if I'm using just one array and that is in no way, shape or form the bottleneck of my application, this is not going to magically make it faster, right? So as always, you have to evaluate first, is this something that alleviates some of the overhead that causes my application to run slow? Next up, we want to look into zero copy techniques. We want to see what the concept is of zero copy techniques, some use cases, some benefits, and again, a practical example of how, when, where to use it, and so on. Those with a C++ background, especially, those might be already more familiar with some of these things. Of the concept of zero copy, because of the way pointers can be handled in C++. You can send an object. You can say, I'm going to send this object by reference, or I'm going to send this object by value. And if you send something by reference, you don't necessarily have to make sure you copy it to everywhere. You can just send a reference to one object into certain places. You can do that with almost any data type in C++, whereas in higher level languages like C#, we do not have that distinction of sending something by reference or by value. We want to essentially, as a concept, transfer data from one part of our system to another without having to copy it there, or without having to make temporary buffers for it. Maybe you can use pointers or reference to that data instead. For instance, where would that be applicable? Network programming, memory mapped files, other Blazor components. We get performance gains out of it, efficiency, and again, lower garbage collection pressure. In network programming, we might send and receive large files without having to copy the data into the user space or the user space buffers. With memory mapped files, we can get direct access to file content as if it were loaded into memory with traditional I/O operations, but we're not actually using these I/O operations. I'm going to see an example on that, because that's a very powerful technique that also a lot of people are not aware of. And in Blazor specifically, yeah, we can probably optimize some data bindings to avoid unnecessary copies, can avoid CPU load, and minimize data movement through these kind of things. One example, something we've already talked about, is span and memory T. We are not making additional copies, we're not making additional substrings and so on. We try to adhere to that zero copy technique and say we have one copy, we're just going to create views on that copy for different areas, and that's good enough. That's one, we're not talked about that. The other thing is memory mapping, as I said. For instance, having a large log or data file that we need to process, that we need to analyze, where we need to look for something. It gives us access to file content as if it were an array with very little overhead. We can use memory mapped files to map the content of a file directly into memory and access a specific portion of that file as if it were an array. And memory mapped file benefits that we don't have any intermediate I/O buffers, And the memory management is done or is managed by the operating system rather than the application. So the application memory footprint stays small. There's no garbage collecting on any of the I/O chunks or buffers that are created through traditional I/O of a file. And very cool is that multiple processes can map the same file. So you can have the same file worked on with multiple processes at the same time. This is especially helpful when you have files that are very large, multiple gigabytes, for instance, and you have multiple processes that evaluate, search for something, look for something in that file at the same time. And we can create view access. First, we have a memory mapped file. We create it from file, and then we create a view accessor that tells us from where to where do we want to have a view onto this file. And after that, we can just use it as if it were an array in memory. We do not have to go through traditional I/O and have access to a very large file and process this. Even, like I said, multiple processes at the same time can go on this, which is not traditionally possible with standard I/O. All right, then the next technique that we want to look at is structs of arrays versus arrays of structs. I want to check out what the difference is, what performance implications this has, and another example. Traditionally, in object-oriented programming, we would have a person. Doesn't necessarily have to be a struct, right? Could be any type of object, could be an object person. It's just a struct here because it flows with the concept of struct arrays versus arrays of structs, right? So whether it's a struct of a person or an object person, it doesn't really make a huge difference in this concept explanation. We have a person, and then traditionally we create an array or some sort of list of that person object, and here, for instance, we can call it people. Traditional object-oriented approach of managing records, for instance, right? We have continuous blocks of memory for each of that struct with the fields interleaved. The other approach, where we say, hey, you know what? If we have, for instance, let's say people as here, as arrays of persons, and we're not interested in most of the data on these people, right? We're interested in the age. Maybe we want to create a graph with plotting the ages of all the people of the 10,000 or 100,000 people or whatever we have into a graph or into a map. And we're really only interested in one property, but every object, every single person has, 100 properties, right? Memory access then becomes very cumbersome, right? Because our memory pointer needs to jump from object to object, and within every object find the reference to where the age is. So that is absolutely not continuous memory access, right? This is jumping around wildly in the heap, trying to find where are all these ages, because they're all on different objects at different memory addresses. So the concept here is to say, what? In order to make this faster, in order for that graph to populate faster, to be printed on that report faster, if it needs to access 100,000 numbers, like ages, right, or height in this case here, we are just going to make, arrays of these ages, of these heights, as integer or double values, and then we can guarantee its contiguous memory access, right? We have an array, which is a contiguous section of memory, and every single age from every person is then accessible directly as it loops through this ages array or as through this double array. And yes, right, this is a little bit counterintuitive when it comes to the concepts of object-oriented programming, right? Because in object-oriented programming, you say, what? We want these objects, right? We want everything as objects and managed in collections of objects. But like I said, this is not something that I would do on every single implementation of every single business problem that I'm trying to solve. This is something where I'm in a situation where I'm thinking, what? I need this graph. This graph needs to plot the ages or the heights of 100,000 people or maybe 1 million people. And I need to see the distribution on this scatter plot. And I need to, I don't want to wait for this graph to, render a minute. Because it takes so long for all the objects to be found and all the data points from these objects to be extracted and plotted. Maybe I can do that a lot faster if I have contiguous arrays and my memory pointer just goes continuously from one address to the next to look at all these values. And then I say, okay, for this particular problem, I'm going to implement it like this, not across the application, for this particular scenario only. We have a lot better cache efficiency, of course. We have a lot less garbage collection pressure, of course. We can, of course, also enable faster parallel processing with this. So there's a lot of additional benefits that we can reap from having this implemented. And again, we have to evaluate first whether this is something that is applicable to our specific application, to our specific bottleneck or not. This is not an across-the-board thing you should do with everything. This is if you have an underperforming application, you identify what the problems are, and then you target these problems with very specific techniques that are applicable to just their individual problems. Example, right? We have, for instance, a struct entry, and that has an ID and a value, and then we create an array of those, and we for each access through that loop and render that entry. Versus we could just say, you know what, if all that you need in order to render is the IDs and the values, that's what we're going to do. We're going to loop with a for loop from 0 to 1,000, because we in this example have 1,000 entries, and give it direct access to these two arrays, and then our access pointer can just sequentially jump from one record to the next one without having to do any seek operations in memory to find the objects and then the interesting property on these objects like ID and value. Next up, we're going to look at Stackalloc. Stackalloc is, well, as the name implies, stack allocation. I'm going to check out what performance benefits and risks we have and some example. Essentially, we want to allocate memory on the stack instead of the heap, primarily for very short-lived data, arrays especially. We want to allocate a fixed smaller size of block of memory during compile time for it. And beneficial is that this memory is automatically freed when the method it is being used in returns. It's ideal for scenarios where we have the requirement for every high performance, low allocation overhead and very small data structures, where, for instance, have a very rapid allocation and deallocation of a very small array, for instance, especially if it's within a render cycle. That happens several times a second or even more often in order to update or calculate something. Performance benefits and risks. Well, we have the performance benefit of having a lot faster performance. We have no fragmentation. The speed is a lot faster, a lot less garbage collection pressure. On the other hand, the downside or the risk is, well, we do have a limited size. The stack size is limited. It is typically around a megabyte per thread in .NET. So it is only suitable for small allocations. Excessive stack allocation, when you're not careful, can lead to what we know as stack overflow, which will crash your application. And it can only be used in unsafe code blocks. So you have to be very careful with your memory management to avoid any undefined behavior. If we want to use this, another example, in Blazor, for instance, in the code section, the stack allocation of my integer array here with 100 of length, I just use Stackalloc to create it, operate on it as normal, as if it was a regular numbers array, and it will be freed as soon as that function returns. There's no difference in using it, right? The only way it differs is the way you allocate it. And again, this is also something where I have to evaluate, is that scenario even applicable? Just because I need an array of size 100 does not mean I should always allocate it on the stack, right? It does not mean every single array that I have I should put on the stack. I have to evaluate, is this array and recreating this array and deleting it necessary? And if so, right, first of all, I could probably do something with array pooling even, but if that's not possible for other reasons, or doesn't help, because the rapid creation and deletion is so overwhelming that I need to go from main memory to stack memory and be like, all right, I need to make this faster. Then I will try this and be like, okay, let's try this, give this a try, see if this enhances my performance, and if so, great. If not, right, then I probably should not be using it. It's, again, every technique that we look at here has a very specific purpose and should not be used as a blanket solution for every underperforming application. Then we're going to take a quick look at LINQ. Yeah, LINQ, we all know what it is. It's very convenient in many cases and helps us deal with data collections, connections to database entries and so on. And it's very convenient, very readable, but it comes at a price. And in most business applications, that price doesn't really affect the performance of applications, right? If you have a standard CRUD operation or a standard CRUD application where just read, update, delete, and create some stuff, then you probably won't be immediately in a bottleneck because it's too slow. However, if you have a very high, number of LINQ usage in your code, especially LINQ queries, especially when you use it in combination with databases, you might encounter that something is not as performing as it used to or as you expected. And that is because it does come with a very, very large performance overhead. Of course, we have the pros that it's very nicely and readable. It's very expressive. Allows us to manipulate collections. Allows us to reduce boilerplate code because it flows very well in .NET, and it's very flexible. It works very seamlessly with various data sources like arrays and lists and databases and so on. But, it does, like I said, has a lot of overhead. Performance does decrease. Memory usage increases. And debugging complexity increases too, because it's very difficult to debug a very complex LINQ statement if you have a lot of linked LINQ statements chained one after the other. And then, a lot of times you find yourself reducing that to conventional code, writing your code, doing your breakpoints, evaluating, and then writing it back into a LINQ statement because it's shorter and looks nicer and is better readable. What can we do? Well, alternatively, right, we can do manual loops. We can use span and memory for views instead of allocating, deallocating stuff. We use struct and value types rather than reference types, and can avoid deferred execution. We have to make sure to use certain execution methods, eager execution methods like toList and toArray carefully. To avoid unexpected performance hits. For instance, just because you have an I enumerable, it does not mean you always just have to toList it. If you're not requiring to toList it for various steps of your application, there's no need to it, and it can stay an I enumerable until you absolutely have to toList it to get access to individual properties on certain items, for instance. But every toList operation is very costly. As an example, we, for instance, have recent activities that we want to get from the all activities, and here we have filtering and grouping and transforming done. We have 5 instances here with usage of LINQ, and essentially we are going to have a nicely written statement here, something that people can just look at and know exactly what's going on by looking at it and what to expect at the end, what to get back. However, if this is something that performs really well, right, we could rewrite this. And yeah, it does look different. It's a lot more code, right? We write twice the lines of code now, but we have only 2 iterations over collections rather than 5. And the data, on the previous slide, we had 5 iterations over the data, or over subsets of the data at least. Now we only have 2. We have also greater control. We have more control over the processing flow. We can add additional optimizations in this way. For instance, we can have early exits in here. The trade-off, yeah, this does require more code and is less readable, right? I can't just look at this section of code and immediately know what it does. I will have to look at, okay, what does this for each do? What does the if statement do? And I have another for each. But this is especially useful where you do something on the UI thread, for instance, and it needs to remain responsive, and the resource usage must be minimized. Then it's like, okay, for this particular one, I will write it out. I will take into consideration that I do have more lines of code for this particular one. But on other LINQ statements, it might be fine, right? Again, not something you shouldn't just avoid LINQ completely and say, I'm never using this again. It has its place, right? And it's very convenient. But if you have something that underperforms and you look into it and you find out, you know what, this operation or this function or this particular part of the code is the culprit, and you have something like this LINQ statement from before in there, try it, right? Give it a try and say, hey, maybe I can split this up. Maybe I don't need to have 5 iterations over my collection. Maybe I can only need 2. And if I write those out and have early exits in it, maybe I'm going to be a lot faster. General garbage collection optimization. Garbage collection is not something we typically worry about in .NET, right? It's not something that we're overly concerned with. We should in certain instances, but most of the time we're just trusting it, right? We're just saying, okay, you know what? Garbage collector is going to do its work, and we're going to trust this. We're going to see an overview, some techniques to reduce that pressure on the garbage collector, and an example. In general, the garbage collection works in a generational approach in .NET, where 3 generations are assigned to objects, 0, 1, and 2. And objects are internally promoted from one generation to the next based on their lifespan or their expected lifespan. So it's a very complex calculation of what generation they're assigned for, but that determines when the garbage collector will even look at them in order to pick them up and free up their memory. It's automatic in .NET, right? We don't have to typically worry about it. The .NET runtime automatically handles memory allocation and deallocation, reducing memory leaks. Reducing but not completely avoiding, right? If you try real hard, you can create memory leaks in .NET too, even though you have garbage collection. So it's not something that is not existent in .NET. There is different garbage collector modes. You can set your application into different garbage collector modes. For instance, you can set it into workstation garbage collection, which is optimized for UI responsiveness, or you can set your application in server garbage collection mode, which is optimized for high throughput in server apps, for instance. There's also a garbage collector or gc.try-start no GC region for very extreme high performance scenarios where you have fixed size allocated memory to operate on upfront and will not be garbage collected at all until you free it up. This is for real-time latency sensitive apps where it's not something typical in the standard business application, but it's not to say that business applications cannot be something that is very extreme, relying on high performance, right? It just really depends on the industry, and sometimes you have to make sure that garbage collection isn't performed on this particular part because this is something that needs to run as fast as possible to meet a certain benchmark, for instance. So again, scenario driven, and depends on the circumstances whether or not you even want to use and look into that. And not something I would in general apply to every single one of my applications. Techniques or general techniques for reducing garbage collector. Well, we already talked about a few of those things, right? Avoid unnecessary object creation, structs instead of classes we can use array pooling, we can make use of that span and memory instead of creating substrings. So all of these things combined will of course reduce garbage collection pressure. We can try to reduce re-renders. Maybe we can render on or re-render only components rather than whole forms, that sort of stuff. We can make sure to properly dispose of resources asynchronously to avoid memory leaks in components. We can try to avoid boxing, and we want to always make sure that we profile and tune our application. We don't want unnecessary objects created. We don't want our garbage collector to have to delete certain things that are not necessary. If we, for instance, operate a lot on primitive data types, we do not necessarily, as I said, want to box them, which means turn them into objects. If they can stay primitive data types, even better. And regular profiling of our application helps us find bottlenecks or find new features that we've implemented that create bottlenecks, right? If you have an application, it's always good to continuously profile the application and say, right now at this state, it performs as such. Now at this state, it performs as such, or certain routines or certain methods, which you anticipate or could anticipate could be problematic. If you routinely measure them and profile them and keep a record of that, you can see how over time either it stays the same and everything is good, or it becomes worse over time and you will have to do something in order to avoid running into a scenario where the whole application just becomes so slow it's not fun for the user to use anymore. And with that, we are nearing the end of the presentation. I do, however, have just a very small example that I put together that gives you a little bit of an indication of if I, have an application, I work with a lot of numbers and I do a lot of manipulation on these numbers. I implemented this once with all of the performance techniques applied and once without. I have a flag up here, run with performance tuned false or true, and we can see how long it takes. And it's essentially vector manipulation, vector calculation with a bunch of numbers that it runs through once with a lot of these optimizations we talked about today and once without. Now, I hope I'm not skewing the results here with having, I have like so many different apps open right now in order for this whole streaming setup to work, right? We have the YouTube app, we have OBS running, I have the streaming app running and all the additional applications. I hope it's not going to falsify what we expect, but let's take a look and we run this with performance tuned false first and see. It's not going to take very long, so we're going to run it a few times and we will have 260 milliseconds to calculate my vectors. Let's see that again. Let's run it 3 times, maybe 257, so 260-ish on average, right, with 3 times. And let's say we turn this on and now run this same thing with the optimization. We're about half, right, or a little less than half. We're 115 milliseconds, and I can run this again just to make sure, 128 milliseconds, and run this again, 113 milliseconds. So yeah, we're about half of the time it takes on a conventional approach, right? A conventional approach is, as I said, creating, recreating arrays, substrings, that sort of stuff, and making these calculations, not renting a pool, just creating arrays all the time, not renting arrays from that pool, and running it through my calculation. If I apply all of these things that I have mentioned today, I'm about at half of the time it takes to do the exact same thing. So we can see, half of the calculation time is a significant change to get to the same result. Now, again, for the user, right, if this was something that the user is waiting for, I am not particularly worried about a user waiting 250 milliseconds for the result versus the user waiting 100 milliseconds for the result. Yes, it's twice as fast, but it's not something that impacts the user. However, is this something that is running? This is running at one time, right? If this is something I have to run over and over many times and on a lot more users, a lot more records, and this goes on a report, and that report needs to create a chart and a scatter plot and that sort of stuff. Yeah, it turns from 250 milliseconds, all right, up to 1,000, 2,000 milliseconds. Then we're in the seconds range, right? Then we have 2 seconds, 3 seconds. Then it becomes a difference, right? If I click something and nothing happens for 4 seconds, is a lot, infuriating for a user, versus if I click something and it takes a second, but then it's there, a lot better, right? So I just have to make sure the scenario fits and I can apply these things, and then, as always, make sure you benchmark in order to find out if it is even something that you want to implement in your application, or if it doesn't help, right? If it doesn't help, then you don't, right? It's not something that you should by default do for every single one of your applications. All right. I want to mention at the end the code staffing division that we have. We're disrupting the world of staffing. If you are interested to learn more about code staffing, please go to codestaffing.com or reach out to one of us. We are very happy to talk to you about it at any time. Please visit our YouTube channel if you haven't. We have a lot more videos on there, code present sessions on there, and so on that we post and that we publish on our YouTube channel. Please check it out. I would highly be thankful if you can do the survey to the presentation. Give us feedback if you liked it, if you didn't like it, what you liked, what you didn't like. If you can use a phone to get that survey QR, it should open up this survey for you in the browser. If you want a free 1-year digital subscription to Code Magazine, then feel free to also snap that second QR under subscribe. It will give you a 1-year free subscription digital for Code Magazine, so you can make use of that. And if at any point you do have questions, feel free to reach out for us. You can reach out to us on info@codemag.com, or if you want to reach out to me directly, you can also reach out to me at otto@codemag.com. And if you have additional questions, unrelated to performance or anything that we've talked today, feel free to reach out as well. We're always happy to help or give information to any questions you might have. And with that, that is it for today. Thank you everyone for tuning in, and hope to see you at our next Code Presents. Have a good day, everyone.